Okay, good morning, everyone. Welcome back to another mechanics tutorial. Today's topic will be stress and strain, right? How do you guys feel about this topic? Is it hard, difficult? Is there anything specific you want me to look at? Okay, no one?
Yes, so you can go over the questions from class.
Just the question. All right. Okay, so someone's saying conversions is probably the hardest. Okay, handling your units. All right, so first let's just get the formulas down. So as you know, we come across quite a few of them. There's force, we know what force is. There's stress, there's strain, there's Young's modulus, tensile strength, factor of safety. First, let's just give you guys a little bit of intuition of what stress is. So when we think about applying forces to a material, let's say this metal rectangular bar here, right? And we're gonna apply a force to this bar. Now, that doesn't really tell us what it does to that bar, right? Let's say we applied a 4 Newton force or a 5 Newton force. That really doesn't tell us what it does to the bar, right? 4 Newtons to this bar versus 4 Newtons to maybe a bigger bar or a smaller bar does something different, right? So we want a way to find out how much does it stress the bar itself, because 4 Newtons is 4 Newtons. And if we apply that to a big bar, a smaller bar, the forces are more stressful for maybe a smaller bar than this bigger bar. So that's why we divide it by area, right? So it's force, the force, or force divided by area. Let's say we were to take this first section here. Let's say there was a force being applied to this bar. Let's see. Yeah. A tensor force, pulling force being applied to the bar. Let's look more closely at this surface, right? So pretend the surface is this square here. Let's divide it up into certain sections. Okay, so that's as neat as I could get, right? So we divide this block up into certain sections. When we apply this force holistically to this bar, straight throughout this entire bar, the force is transferred along this bar. So you can pretend this bar is kind of like salami and you slice it up. There are a bunch of different slices. And one slice would transfer the forces, right, onto another slice. So it's transferred along this bar. And you can think of this piece here as just one slice, right? Now, this pulling force here is distributed throughout the bar, throughout the cross-sectional area. So each of these would have a vector coming out of it, right? A vector coming out. So the reason we divide the force by the cross-sectional area is to tell us how even, assuming the force is distributed evenly, is how the forces is distributed throughout the particles in this bar. So we divide it by areas. So we can say, let's say 4 units, 4 newtons, and each of this was some unit of area, let's say 1 unit each, right? Then each of these little squares here, square, maybe square 1, square 2, 3, would have 4 divided by 9 newtons of force affecting them, right? So that's what stress is. Stress tells us how the force is distributed throughout the bar, right? And of course, these forces here are transferred, right, from section to section within the bar. And it propagates throughout the bar. Right? So that, in essence, is what stress is. Right? Force divided by area. And that's what it tells us, how evenly the force, how the force is distributed throughout the bar. All right, now strain. Yeah.
So isn't force basically just pressure?
Stress basically just pressure.
Yeah, because pressure is force over area.
Yeah, so this is why I wanted to define what stress is specifically. Now, pressure, yes, pressure is we're applying a force and we're applying that force over a particular area, right? So now, let's say here, this bar maybe has a hook or something, right? And you would apply a rope and we pull, right? Now, pressure is something like, let's say there's a container, right? And we have some water inside, and the water would apply it over this surface area, right? So it's same force of area, but this here is we're applying the force onto this area, right? The force is being applied onto this area. So it's pressure. But here, we're saying the force is distributed throughout the bar, and the force propagates throughout the bar, and the cross-sectional area of the force, of the cross-sectional area that's normal to the force is stress. Right? That's the difference. It's like this here, it's inside the bar, like inside the bar, and this here is like on the surface. Does that make sense? Pressure is like pressure is like on the surface, and stress is like internal stress of the bar. Right? It's different. Stress is internal. We're talking about how does this behave on the inside, right? Because this force obviously could be coming from some kind of hook or something welded onto the bar. So the area here is different, right? So what we do is we take the area that's perpendicular to the bar. So as you learn math and you learn more about vectors and cross products and stuff, they can be like perpendicular areas, and you learn like double integrals, which is like surface integrals to integrate along the surface, and you're gonna find vectors coming up normal to the surface and things like that. And it's gonna become more clear. But stress is not pressure, right? It's not the same formula, sure. Yeah, but stress is not pressure, right? They're different things. If it was pressure, we would just call it pressure, right? Good.
Okay, so
Good. Now strain. So strain, we know strain is equal to the change in length. So let's say delta length, right? The change in length divided by the original length. And this is useful, of course, because let's say we had a bar or a piece of wire that was 25 meters long, and by stretching it, applying a force, right, it elongated, it extended 1 meter. That's different from having a bar, let's say 100 meters long, and that being extended 1 meter, right? Here, the strain was more on this because this is technically 4% elongation versus this just being 1% elongation. So the strain here is more, yeah, because of course it's a shorter material, it's a shorter piece of material. So percentage-wise, it's being stretched for more. So this is how we quantify this elongation, by using strain. So instead of just saying, okay, it elongated 1 meter, but what does that mean in terms of the material, right? What is this 1 meter means in terms of the material. What percentage of that material is being stretched? So it would vary from a 25-meter span of wire to a 100-meter span of wire. Right? So this is why we come up with this formula. Help us quantify what that elongation means. Right? The same way with stress, right? We can't just go about using the 4-Newton force, right? Because a 4-Newton force on a big bar is different from a 4-Newton force on a smaller bar. So the way we quantify those forces with relation towards the material, towards the bar or the length of wire, is by defining them in terms of stress and strain, right? So the formula for strain is change in length divided by length. And for stress is force divided by cross-sectional area. All right, good. So this is how we define things like forces and changes in length, extensions, or elongations in terms of the material, in terms of the body, right? Okay. Okay. So another thing, let me go over quickly. So if you guys remember, maybe from CSEC or CAPE, came across something called Hooke's law. And what Hooke's law stated is that when a force is applied to something like a wire or a spring, the amount of extension we get, so when a force is applied, to a spring or something, the amount of extension we got is proportional to the force. So force is proportional to extension, right? Now we can always write that as 4 is proportional to extension, right? And that's Hooke's law. So what Young's modulus is, it's an extension of that. Well, not extension like this, but it's kind of a more advanced version of it. And we say E, so instead of this constant K, which we define if we apply a 4-Newton force, this extends a few millimeters, right? That this constant would define that, right? Would define the changes between the force and the extension, right? So Young's modulus is E. So imagine this constant here. Solving for K, we get K is equal to the force divided by the extension. But in Young's modulus case, remember, we don't want to use just forces and we don't want to use just extension. We want forces, but what exactly does that force mean in terms of the body, right? So we want to use stress. And we don't want just extension, but we want what does that extension mean in terms of the body? So we use strain. Yeah. Now, it's pretty similar to this constant, but it's like on a higher level. So this is Young's modulus. We call it E, or we use the letter E to represent it. And the formula for it is stress divided by strain, right? And it's just an extension of Hooke's law. Okay, good. So those are the three forms we're gonna work with for now. And as the others pop up, we're gonna look at them. All right, let's start off with number 10, I think. No, actually number 8. So number 8. A steel rod, 10 millimeters in diameter and 3 meters long, stretches 1.8 millimeters for a pull of 10 kilonewtons. Calculate the value of Young's modulus for the steel. Okay. So steel rod, the diameter is 10 millimeters, right? So the diameter of this is 10 millimeters, and it stretches for 10 meters. No, 3 meters, sorry. So 3 meters long, right? Now we know stress, so we're trying to find Young's modulus, right? Young's modulus is stress over strain. Yeah, Young's modulus, stress over strain. So what's stress? Stress is force divided by the cross-sectional area. So we know the force is 10 kilonewtons from our question. And the cross-sectional area we can find out by means of this diameter, right? So what's the formula for the area of a circle? Well, that's pi r squared, or sometimes you might see pi over 4 d squared, which is just the same formula. So pi r squared, right? The steel rod, 10 millimeters in diameter, right? Converting to meters because we want to keep it simple, right?
Oh, Scott.
So this 10 millimeters in terms of meters goes to 0.01 meters, right? Divide by 1,000. 1, 2, 3, right? 0.01 meters, right? So the formula is pi r squared. Pi r squared. Now this 0.01 meters is the diameter. So the radius we got divided by 2, right? So 0.01 divided by 2, that's the radius. So that's what we do here. Cross-sectional area is pi times our radius, 0.01 divided by 2, right? Because 0.01 is the diameter. And we square that, plug it into a calculator. Now what we're going to find is that we end up with a really small number. Really small number. Let me plug it into the calculator. So 0.01 divided by 2. What did I divide it by? 0.01 divided by 2 equal to 0.05. Square that. 0.025 squared equal to that times pi, which is that's 3.141. Close enough approximation for pi. We get this answer. 0.000078538. So let's try and standardize that to make it a reasonable number. Instead of writing 0.000, instead of writing 0.0000785, what we do is write it like this instead, right? So write this as 78.54 times 10 to the minus 6. So what is 10 to the minus 6 tells us? A negative power, right? 10 to the minus 6, this negative power, that means 1 over 10 to 6. So it's kind of like dividing this number here by 1,000,000, which would give us back this number, right? So this here is notation you would have come across. I think they call it scientific notation in high school. Does everyone
One
understand
question,
this
sir.
notation?
Yes, I saw one question, sir, right?
Yeah.
So what was my question? Yes, so when you have to write the answer in scientific notation, isn't the point supposed to be in behind the first natural number?
Well, you write it how you want to write it. So
Okay.
maybe at like the CSEC level, they would want you to write it as the first number, but you write it at the number at the point that's comfortable for you, right?
Okay, so if write it in any ways, I'm going to get it right.
You could write it like this if you want, 0.00078 if you want. Yeah, that's fine.
Yeah, because I see Miss Sam get 0.7854 times 10 to the minus 4.
Yeah, because for her, -4 is a good number, but I like putting it as multiples of 3s because it helps me out with like meters and millimeters and pascals and megapascals, and we're gonna see, right?
Okay.
Yeah.
That's that.
Yeah. Okay. So stress is this force times this thing we just find, right? It's not the force times this force divided by this cross-sectional area. So we got that here. Let me see, there's some questions in the chat. Will we ever use irradians in MEC? Steve. Yes, we will use irradians in MEC. Maybe next semester you guys will use irradians. All right. Okay, good. So stress is equal to force divided by this cross-sectional area. So the reason why I like keeping it in multiples of 3s is for things like this. Let's say this 10 kilonewtons, right? That I could write that as 10 times 10 to the 3, right? And here what I got is 78.54 times 10 to the minus 6, right? So this I know would work out to something like whatever these two numbers divided as by times 10 to the 9, right? That's how it would work out for me in my head. Like I can just carry this up, and I know this can change that plus sign using some stuff you learn in math about powers and things like that. So for me, keeping it in multiple 3s is fine, and I can know my answer is 10 divided by this times 10 to the 9, right? And that's easy for me. Mm-hmm. For you, you might like it, maybe you did it. Keeping this as 10 to the 4, right? And writing a number like 0.7854 times 10 to the minus 4. And that's fine. And you'll still get the same answer, right? I like keeping it in multiples of 3s. Okay, so we divide this out from a calculator again, right? And we get this long number here, right? So we know pascals, Newton meter squared is equal to a Pascal, right? 1 Newton per meter squared is equal to a Pascal. So kilonewtons per meter squared is obviously kilopascals, right? That's kilopascals. And meganewtons, or 1,000 kilonewtons, 1,000 kilonewtons per meter squared is equal to megapascals, right? And you can go up 1,000 times 1,000 megapascals is equal to a gigapascal, right? 1,000 megapascals equal to a gigapascal, right? So you guys want to take out your calculators and try multiplying this out here. Maybe put in So take out your calculators, divide this out, and tell me if you get an issue filling it out. If they may be the notation or just handling small numbers is difficult. So divide this number, right? And tell me if you have the same thing. Okay. Yeah. So if anytime along the way you don't get the same answer when you are working it out, stop me and I'll go through it, right? So after finding this answer for stress, we had as 127.324 megaparscals.
Yes, sir. Yes, sir. Yeah, that's correct.
Good. And I know that the conversion can be difficult sometimes, but you know, with practice, it'll come and you'll start finding easier ways to manage your numbers. And you know, if it's too difficult, just keep the numbers whole, keep it at small places, and plug them back into your calculator, and the calculator will do the hard work for you, right? You don't need to manage all your powers and things like that, right? So let the calculator do your work if you find it difficult to calculate and manage the conversions. All right, good. So we found stress as 127.324 megapascal, right? And we know pascals is just meganewtons per meter squared, right? We divide this by 1,000. Now, again, the question asks us to find Young's modulus. So E is equal to stress over strain. We found stress, but what is strain, right? Well, strain is that change in length divided by the original length. So what is the change in length? 1.8 millimeters. So 1.8 millimeters, well, we divide that by 1,000. Divide that by 1,000 and we get 0.0018 meters, right? And what's the length of this steel rod? Well, the length of this steel rod is 3 meters long. So 0.0018 divided by 3 meters, that will give us 0.0006. Or, if you want to write it in scientific notation, or we can write that as 6 times 10 to the minus 4, right? Because maybe 6 is an easier number for you to handle. Or alternatively, we could write it as 0.6 times 10 minus 3, which is also good, right? Now, strain is a unitless term. It's just a term that defines the elongation with respect to the material, right? It's unitless. Okay, good. So alternatively, you can convert this to 3,000 millimeters, right? 3 meters to 3,000 millimeters. And do 1.8 divided by 3,000, and you'll get the same answer, right? So this is unitless. These meters cancel out. So as long as they're both in the same units, you should be fine. Now, this and this, we found stress and we found strain. Let's divide them, and we should get Young's modulus, right? So let's divide them. So this is in megapascals, and this is unitless, right? So this is in megapascals, remember that? And this is unitless. So 127.324 megapascals divided by unitless value 0.0006. We get this big number, right? We get 212,206, right? So 212,206, 200. 212,206 megapascals. And if we divide it by 1,000, we just end up with 212 gigapascals, right? Any questions? I know the numbers are large, and some of the numbers like strain are small, but any questions overall? No.
No, sir.
Continue on. As long as you manage your numbers, this stuff should be easy, right? So number 9. It's pretty similar to number 8. So let's continue. A steel rod, 20 millimeters in diameter, is subjected to a pull of 40 kilonewtons. Calculate A, the stress, B, the strain, and C, the total extension on a length of 200 millimeters, assuming E to be 200 gigapascal. E in this case is Young's modulus. So what do we need to find? Stress. That's part A, the stress. The formula for stress is force divided by cross-sectional area, right? What was the force? The steel rod, 20 millimeters in diameter, subject to a pull of 40 kilonewtons. So the force is 40 kilonewtons. What's the cross-sectional area? Well, it's the steel rod of diameter 20 millimeters. So the 20 millimeter diameter should tell us the cross-sectional area. So using this 20 millimeters in diameter, right? Converting this to meters, because we want to manage our units well. So that becomes 0.02 meters, right? It's a diameter, so it needs to be a radius, 0.02 divided by 2, right? So this is our radius here. We can, of course, break this down even further to 0.01, and then we put that into our formula, right? So this is our radius here. So the cross-sectional area is pi r squared, pi times, open bracket, 0.02 divided by 2 squared. Plugging this into a calculator, we'll get a really small number, right? We'll get 0.000314 31416, right? We get this number. And of course, putting it into a number that we would like to handle instead of punching all these zeros into our calculators, we just multiply it by 10 to the minus 6. Of course, you can choose another value that's useful for you, or you can choose to not put it in this notation at all. Whichever one works for you and helps you solve your problem. You get. So keeping this number like this, and we know that the pull is 40 kilonewtons, we can calculate stress. So the stress is 40 kilonewtons, and we divide that by the cross-sectional area, we should get 127,324 kilopascals, because the unit here, kilonewtons divided by meters squared, and that's kilopascals. Kilopascals, Newton meter squared, right? Yeah. Dividing that by 1,000, we get 127.32 megapascals, right? Maintaining our units. So next, part B, the strain. So we figured out the stress. Now it's time to figure out what the strain is. So they gave us Young's modulus, they gave us E, right? Assume E to be 200 gigapascals. So if we assume E to be 200 gigapascals, then this 200 gigapascals, GPA, like grade point average, equal to stress, the stress we just found, 127.32 megapascals, right? MPa, divided by strain, which is our unknown, what we want to find. Now, this gigapascals, right? This is 10 to the power of 9 giga, right? So K is 10 to the power of 3. Mega is 10 to the power of 6, right? And giga is 10 to the power of 9. So just memorize these, right? Okay. So this here is 200 times 10 to the power of 9, and mega is times 10 to the power of 6, right? So we can just change all of those into pascals, right? So 200 times 10 to the power of 9 pascals is equal to 127.32 times 10 to the power of 6 pascals divided by strain. Solving for strain, we get strain equal to 127.32 divided by 200. Let me get some space here. This here, this is times 10 to the power of 6 divided by times 10 to the power of 9. Okay. Plug this into our calculator. We should get strain is equal to 0.000636, right? Maintaining this. An easy way to do it, how I do it, is we remove this power from here. So this here becomes, put this down here. Hope you guys following, and I'm not writing too scrawly, right? 127.32 times 10 to the minus 3, right? Divided by 200. Now, how I get this minus 3 is I move this here, this base on this power, this 10 to the 9 to the top. So when we change it from the denominator to the numerator, right, it becomes this, that 10 to the 6 here. That here is times 10 to the power of minus 9. If you guys know this rule. So then this here would simplify to 10 to the minus 3, right? Because we add the powers here, right? So 6 plus minus 9 is minus 3. So whatever these values evaluate to, this 127.32 divided by 200 is times 10 to the minus 3. So let's put that into our calculator real quick. So this here is equal to 127.32 divided by 200, right? So 0.6366, 0.6366 times 10 to the minus 3, which is this, right? Which is this. So we're good there. Now we found strain. Okay. Now using strain, to find now the extension, we know strain is equal to that extension. Strain is equal to that extension or change in length, right? That extension or delta L, change in length, divided by the original length. The original length from the question is 200 millimeters. So the length is 200 millimeters. So we can find the extension in millimeters, right? And no need to change it. So keeping this strain 0.006366 equal to the extension divided by 200, multiplying this by 200, right? We get 200 times 0.006366 0.06366. This moves to 2 times 0.06366, and this goes to 0.12732. Okay. And this here is in millimeters. Any questions overall? Are you guys getting the same answers while you're working along?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So as long as you guys getting the same answers, they're moving faster. Okay.
One question, so right?
Yeah.
One question. Say, what I noticed, right, is that they didn't strain. I know strain is equal to extension over its original length, right?
Yeah.
But like the first question, they gave us two length. They gave us 1 millimeters, 1 meters. But in this
Yeah.
question, the John just give us one length, which is
Yeah.
in millimeters. So we could use that to the original length too, the same millimeter.
Yeah. So what's important to note is that strain, right? Strain. What are the units for strain? Strain doesn't have any units. So whatever this length is, let's say the extension was 5 meters and this here was 10 meters, right? These would cancel out, yeah? The meters would cancel out. So same with millimeters. If it's 5 millimeters and 10 millimeters, this here would cancel out, right? So strain's a unitless term. So whatever you put the top in, you should put the bottom in, right? So essentially that's how it works. The unit should be the same. So like in the question, right? They gave us 200 millimeters. So what we got to remember from this is that the answer we get is in millimeters, right? The answer is in millimeters, and not to make the mistake of putting meters. So yeah, if they give you two lengths and both of them are in meters, then great. If they give you two lengths and one of them is in meters and the other is in millimeters, then you got to convert, right? You got to convert from meters to millimeters, right? So just make sure whatever the top is, the bottom is, and whatever you put in, that's what you're finding, right? If you put in millimeters, you're going to be finding millimeters, right? Good. So number 10. A body having a mass of 1 megagram is attached to the lower end of a vertical aluminum rod, 30 millimeters in diameter and 2 meters long. Calculate A, the stress in the rod, and B, the extension assuming E to be 70 gigapascals. So this body weighs 1 megagram. So 1 megagram is equal to 1,000 kilogram, right? Or 1 megagram is equal to 1 times 10 to the 3 kilograms. Yep, makes sense.
Sir.
Yeah. Someone asking a question?
No, sir. Just agreeing with what you're saying.
Okay. Okay. All right, good. So 1 megagram is 1 times 10 to the 3 kilograms. So therefore, the weight of the body, multiplying it by our gravitational constant, 9.81, and the weight of the body, the mass of the body is 1 megagrams, right? So that's 1 megagrams times 9.81. 9.81 though we know that is used for kgs, right? Is newtons per kilograms, right? Kilograms. Yeah. 1 kilogram gives us 9.8 newtons of force, right? 0.8. So 1 times 10 to the power of 3 times 9.81 is equal to 9.81 times 10 to the power of 3 newtons, right? Or alternatively, we could write that as 9,810 newtons, right? As the weight of the ball. Either way is fine. Okay. So we have the force, and we're asked to calculate stress. So stress, force divided by cross-sectional area. Again, it's another aluminum rod, so the same thing we've been doing. 30 millimeters in diameter is 0.03 meters. Remember, it's a diameter, so we need to divide by 2. 30 millimeters in diameter is 0.03 meters divided by 2 as a radius. Plugging that into a formula or pi r square
Sir,
form. Yeah.
if it's mega, it's now 1 times 10 to the 6
If it's what? So,
mega.
okay, yeah, good question. So 1 megagram is equal to 1 times 10 to the 6 grams, right?
Oh, you use kg.
Good. But the gravitational constant, right, 9.81. Remember, as engineers, we did the experiment and we found out that 1 kilogram exerts 9.8 newtons of force. 1 kilogram, right? Not 1 gram. So this gravitational constant is newtons per kilograms, right? So that's why we use 10 to the 3 instead of 10 to the 6.
Yeah,
Good.
I get you. Go back to the base units.
Good. So the cross-sectional area, pi times 0.3 meters divided by 2, making it a radius squared, should give us a small number, and we make it manageable, right, by 10 to the minus 6, right? So that should give us 706.86 times 10 to the minus 6 meters squared. Meters squared. Okay. Now, we calculated weight, so our force, and we have here the cross-sectional area. So putting that into a stress formula, we get 9.81 times 10 to the 3 newtons divided by 706.86 times 10 to the minus 6 meters squared. And here we can see how this notation can be particularly useful, because what we can do is we can take this to the top and make this 10 to the power of 3 plus 6. So this here becomes 10 to the power of 9. So when we divide these two, we multiply that by 10 to the power of 9. And we can, of course, that answer would be in pascals. So whatever this answer here, let's say this here divides to A, this part here divides to A, we get A times 10 power of 9 pascals, right? Pascal. Right, Pascal. So let's put that into our calculator real quick. Managing our numbers again. 9.81 divided by 706.86. Get it accurate. We have 0.013. Write that down. 0.0138788. Okay. 0.01388. Good. And this is times 10 to the power of 9 pascals, right? So this here would be 0.01388, 10 to the 9, so that's gigapascals. Or taking off 1,000, right? We get 13.88 megapascals. pascals. So manage a unit as you think is necessary and come up with reasonable numbers, right? Answers. So what I used was megapascals, so 13.8 megapascals. And again, alternatively, you can just plug this into your formula, plug this into your calculator, sorry, right? And just get a number out. Notice that the units is newtons per meter squared, and then write that down as megapascals or whatever, right? Putting everything into your calculator instead of keeping this 10 to the 3 and 10 to the minus 6 and doing 10 to the power of 9 outside, right? So we just found stress. We make some space. Good. So just calculated stress, and now we want to calculate extension. We know extension comes from strain, so we're given Young's modulus E. We're given Young's modulus E as 70 gigapascals, and we know here stress is equal to 13.88 megapascals, or 0.0138 gigapascals, right? Strain. So you see here, it would be useful to just keep both of them in gigapascals, right? Instead of putting this in megapascal. So it might be useful to just have found this answer in gigapascals in the first place to make calculations here simpler. So as you go through, you'll find whichever way is easiest for you, right? Good. So dividing these two, we find strain to be equal to 0.1983 times 10 to the minus 3. And the way we get that is because this here is megapascals, right? And this is gigapascals. So this here is, let me just write the exponents, is times 10 to the power of 9 is equal to 10 to the power of 6 divided by strain, right? Carry strain over here, take 10 to the 9 here. So when we move this 10 to the 9 up, this would be minus 9. So it's 10 to the minus 3, managing on our exponents. So when we divide these two, this here, this 18 and this 70, we get this times 10 to the minus 3 because that's our units cancel out, right? And give us this 10 to the minus 3 as strain. Now, having found strain, putting that into our formula for strain, which is extension or elongation or change in length over length, we get the same 0.1983 times 10 to the power of minus 3 is equal to that change in length divided by 2 meters. And 2 meters was given to us as the length of the rod. So solving that for change in length, we get change in length is equal to 0.397 times 10 to the power of minus 3 meters. Or, now this 10 to the power of minus 3, right, is involved with it being meters, right? So if we move that away, essentially, this number here, essentially multiplying it by 10 to the power of 3, multiplying it by 10 to the power of 3, we get 0.397 millimeters, right? So 1 meter is equal to 1,000 millimeters, right? So we multiply by 10 to the power of 3. So this here gets dropped off. So we get 0.397 millimeters. Yeah. Now, any questions again? No. Well, I want you guys to take a look at 11, work it out, and tell me if you have any problems, right? So when a metal block is suspended by a steel wire 5 meters long and 2.5 millimeters in diameter, the elongation 3 millimeters. Calculate the mass of the block assuming E to be equal to 200 gigapascal. So now, a few things are different, but you guys should be able to figure it out, right? So take, let me say, 10 minutes, work this question out, and tell me if you have any difficulties along the way. All right? Are you guys coming along? Getting through?
Yes, sir.
All right. So I think that was 10 minutes. Is anyone finished?
Yes, sir.
You got the same answers?
Yes, sir.
All right.
Yes.
Anyone else? Yeah. Good. So any
Yes,
questions?
same answer.
So no questions since everybody had the same answer. Oh, one guy said he used the wrong length. Use the right one now and should be fine. So it's good. Unlike the other topics, all the topics that we had when we first started, it doesn't really require any visualizations or diagrams or anything like that. You know, as compared like moments where you'd have to draw out the diagram to really see what's going on. Or maybe with a ladder problem, the ladder leaning against the wall, right? You need some diagrams for that. But this is just hard calculations and your formulas, right? You got your formulas, just do your calculations and you're fine. All right. So I'm not gonna go through 11 since it's just pretty much the same thing from before. The only thing different is mass. So we're dividing by 9.81 here, and this is something you would have done before in the previous topics, going from force to mass divided by 9.81. Okay, nothing new. Number 17, because you guys have a test Friday. You guys have a test Friday, so what I want you to focus on is number 17. Okay, and possibly number 18 also, right? So if you weren't paying attention, maybe try paying attention now. Number 17 and number 18 for the test, right? Yeah. A steel rod, 10 meters long and 3 meters in diameter, is subjected to a pull of 600 newtons. Calculate A, the stress, B, the elongation. If the modulus of elasticity is 210 gigapascals, C, the factor of safety if tensile strength is 500 megapascals. All right, good. So this steel rod is 10 meters long, 3 meters in 3 millimeters in diameter. So the diameter should tell us the area, and we can find stress, which is part A to the question. So force divided by cross-sectional area. Let's skip some steps now because we've been working some questions, so we're familiar with how this thing operates, right? So the pull is 600 newtons. So the force is 600 newtons. So stress is equal to 600 newtons divided by that cross-sectional area. We know our diameter is 3 millimeters. We know 3 millimeters is 0.003 meters, and this is 0.003 divided by 2, moving from meters as a diameter to as a radius, right? So this is the diameter, and this is the radius. We plug this into our pi r square formula, right? We get pi times 0.003 meters divided by 2, and we square that, right? Plug all this into our stress formula, 600 newtons divided by pi times 0.03 divided by 2 squared is equal to 84.883 megapascal. Right? And that's stress. Now, they gave us the modulus of elasticity, and what that is, that's just another way of saying Young's modulus, right? Modulus of elasticity. It's not a way of saying Young's modulus, right? And we know Young's modulus is equal to E. Young's modulus is equal to stress over strain, right? Over strain. We just found stress as 84.83 megapascal, right? And Young's modulus was giving to us as 210 gigapascals. So transposing, we get strain is equal to 84.883 divided by 210. Times 10 to the minus 3, right? Because it's gigapascals divided by megapascals. And this here is equal to, when I plug this into our calculator, we have 0.4042 times 10 to the minus 3, right? As the strain. So now using the strain to find elongation or extension or change in length, we know the strain 0.402 times 10 to the minus 3 is equal to elongation divided by length, right? And the length is 10 meters. So now we don't need to convert or anything or put in millimeters because we're finding elongation. So what we just need to make a note of is that the answer we get is going to be in meters, right? So solving for elongation, extension, delta L, or maybe you can call it EXT, extension, is this 0.4042 times 10, right? Times 10, hold on. Let me erase this there. Times 10 to the minus 3 times 10, which is this 10 meters, right? So this here becomes 10 to the minus 2. 10 to the minus 2, which is 0.00404.2 meters, right? Meters. Now, 1 meter is 1,000 millimeters. So just multiply this by 1,000, right? We get 9 millimeters. So 1, 2, 3. We get 4.042 millimeters, right? Now, the third part of the question, which is new, is the factor of safety if tensile strength is 500 megapascals, right? So what is tensile strength? Well, let's look at Young's modulus again. Young's modulus, we know Young's modulus describes the material, how it reacts to stress, how it elongates, extends, or compresses as a result of stress, right? We know that stress over strain. What tensile strength is how much can the material withstand, right? So tensile strength, just like how Young's modulus would vary from materials, steel would have a particular Young's modulus, right? A particular modulus of elasticity, so would aluminum, so would lead. Kind of similar to how we had it with coefficient of friction, right? So steel, aluminum, lead, glass, concrete, beech wood, right? Along the grain and across the grain, depending how we apply the forces, would have different moduluses of elasticity, right? Now, tensile strength is something that also varies by material. Let me see if I can get a chart up. Maybe this isn't the best. What the tensile strength tells us is how much stress can this material withstand without breaking apart or splitting in two or deforming, right? That's what tensile strength tells us. There's also things like yield strength and ultimate strength that you guys will come across throughout your engineering lives. But different materials, something like bamboo, or concrete would have a different tensile strength, right? And that tells us how much force you can apply to it before it breaks, right? So 2 to 5 megapascals is the tensile strength for something like concrete. So when you're building a bridge or something like that, and you're using a piece of cable, or you're using a piece of cable on your bridge to pull something or hold something up, you want to know, okay, how much weight can this piece of cable hold? What's the tensile strength of this weight, right? Of this tensile strength of this piece of rope, because you don't want the rope to break, right? Because what happens if the rope breaks? Well, the thing would fall down, and that would make your design particularly unsafe, right? So you don't want the materials to break, or you don't want stuff to fall on people, and you don't want your whatever thing it is you're building, if it's a bridge, a house, or maybe it's a roof, and you got some wood, you don't want it to collapse in. So you want it to be a particular range away from that ultimate failure point, right? You don't want the load you put on it to be equal to the tensile strength, right? So the tensile strength, the ultimate tensile strength of this material, 500 megapascal. So that should give you an idea what kind of material it is. It's a steel tie rod, and that is the tensile strength of it. So it is a particularly strong piece of steel that it could handle 500 megapascals. Now, the factor of safety, it tells us, it's a number that tells us how safe is this system, right? So if tensile strength, give me a second, please. Yeah, so if tensile strength is 500 megapascals, 500 megapascals, let me remove these other distractions here. 500 megapascals. And the stress we put into the system, the forces we apply, how we stress the material, is also 500 megapascals, right? What's going to happen is that this thing is very likely to break. So the factor of safety is 1. So it's you ever heard someone say this thing is 1 times as safe? Like, it's not really a good number. So with a factor of safety of 1, right, that means the tensile strength is equal to the stress we're allowed to put on a system. So this is not very safe, right? So what the factor of safety tells us is how much more safe the system is than the forces we're allowed to put on it, right? So as we reduce the allowable stress, the maximum allowable tensile stress or permissible tensile stress, let's say we reduce it and we say, okay, I don't want big trucks driving on my bridge because trucks are very heavy and they would exceed my permissible tensile strength. So we want to say maybe only things that are less than 400 megapascals. Now, we see this number goes up, right? We see this number is now 1.25, right? 1.25. So when the factor of safety goes up to above 1, it becomes safer. And when it's 1 or less, it's unsafe, terribly unsafe, right? It's pushing that limit. So the factor of safety tells us how safe we are. And there are certain standards in place that use the factor of safety, say, don't surpass this factor of safety for particular construction, right? And you guys will come across that as you go on. That's what factor of safety is. It's just a number that tells us how safe the system is with respect to the forces that we're going to be applying in the system. Okay. So the formula factor of safety is tensile strength divided by permissible tensile strength. And factor of safety, or safety factor, sometimes, just a number that tells us that. If the number is 1, no game, that's bad, right? More than 1, more than, no, that's less than. The number, the safety factor, If that's more than 1, then that's good, right? More than 1 is good. 1 or less, bad. And that's all to it. Good. So the tensile strength of the material, we were given as 500 megapascals. 500 megapascals. And the permissible tensile strength, well, we don't have that, but we know the stress we put into the system, right? The stress we apply to the system. The stress we applied to the system was 84.83 megapascals, right? It was 84.83 megapascals. So using that, we can find what factor of safety is the system currently operating at. And we see the safety factor is 6, which is good. Well, almost 6, which is good. Good. That means it's very far from its limit, right? Safety factor is 6. 6 times away from its limit. It's not very close to this 500 megapascal limit. If we were to apply more stress and it would reach that, then the steel bar would break, right? So we're at the safety factor of 6, which is good, and this system isn't nearing breakdown or at a area where it would collapse or anything like that. Any questions on this? So for factor of safety or safety factor, just use this formula: tensile strength divided by permissible tensile strength. What's the best safety factor? So it would vary. It would vary. Obviously, you wouldn't want to be 1. So there's certain standards in place. So there's certain standards in place that, you know, building standards is like the Guyana Building Code and things like that. And as you start building bigger structures, you're going to come across these standards and they're in there. I can't say what the best safety factor is right now because it would depend on what you're building, right? So, or you could be, even like for me as an electrical engineer, you're an electrical engineer and you're pulling wire, right? So you guys know cables, the high voltage cables outside, right? And there's a tower here, like a distribution tower here, right? And there's another distribution tower here, right? When we draw wires across here, right, there's an amount of tension we're allowed to put on them, right? Because the tension would affect, as you pull it, that would affect the cross-sectional area. And in electrical engineering, cross-sectional area is tied into resistance. So like V is equal to IR, you guys know that resistance? So if the cross-sectional area affects the resistance, we wouldn't want to stretch this wire too tight because that would affect the resistance of the line, which would affect current flow and voltage and things like that, right? So it depends, right? You could go from being electrical engineer to resistance area, worrying about tension that way, right? Worrying about tensile strength and yield strength, which affects the area, right? Or you could be as a civil engineer, like you're building the Denmark Harbor Bridge, and you remember the bridge open, so there's a pulley system and the cables in place there. So the safety factor there might be very different, and you could be building a really large building and there are your beams in place. So the safety factor there is different. And then you could be someone designing a car. Safety factor there is going to be different, and designing a plane, safety factor there is going to be different. So from electrical engineering to aeronautical engineering to mechanical, to civil, whatever it is, there's standards in place. If you got a specific standard in mind, I can, or a specific application in mind, I can check for you and get back to you. But it varies, yeah? Yeah, it varies, depends on what kind of application you want to put. So the safety factor here, electrical engineering is not that big, but maybe for a bridge is more intense, and maybe for a plane is more intense. And it also is affected by how much money you want to spend. So and what materials are available, right? Maybe steel is very strong, right? But it's expensive, so you know the tensile strength would change if you use something that's not steel. If you use wood as opposed to steel, and that would depend on the application. Are you building a house or are you building a 5-story building? Okay, so it would vary. Yeah. So that's just safety factor is this number. Yeah. That's it really. Find a standard that applies to what it is you're building and follow that standard. Okay, good. So number 18. No questions on number 17, right? Okay. Oh, this is actually the thing I was talking about just now. So an overhead conductor of an electric transmission line is a hard drawn copper wire 10 millimeters in diameter, having a tensile strength of 320 megapascals and a Young's modulus of 110 gigapascals. Assuming a safety factor of 6, calculate A, the max allowable pull on the wire, and B, the corresponding elongation on a span of 50 meters. Okay. So this is the same thing I was talking about here. There are two towers, 50 meters in between them. There's a certain amount of tension we're allowed to apply on this line without it affecting the wire, the dimensions of the wire, causing this wire to stretch. Okay. Okay. Good. Yeah, assuming a safety factor of 6, calculate A, the maximum allowable pull on the wire, and B, the corresponding elongation on a span of 40 meters. So factor of safety factor again is tensile strength, which is the breaking point of the material, or sometimes you might not want the material to stretch, so you might go something like yield strength, right? Yield strength, why? Yield strength, yeah, yield strength. And other things like ultimate strength. But for this class, we're just gonna look at tensile strength, right? We're just gonna look at tensile. Okay, so factor of safety tensile strength over permissible tensile strength, or the stress that we are putting into the system, the stress we're putting into the system, and we want to see whether or not it's safe to put this stress in, right? Whether or not it's safe to apply this load. Right, good. So the wire, the copper wire, has a tensile strength of 320 megapascals. Great. We assume the safety factor of 6, which is maybe a standard. Maybe they say when drawing wires, we want to have a safety factor of 6, right? Good. So what's the permissible tensile strength? So the max allowable pull, so we know pull is a force, right? Pull is a force. So forces is just like the simpler version of stress. Right, good. So we need to find stress to find force. So the permissible tensile strength is 53.33 megapascals. We just divide 320 megapascals by 6, right? Divide this by 6, we get 53.333 megapascals, right? Again, remember, force is just, stress is just a more advanced version of force, right? Force divided by the cross-sectional area. So using the stress we just found, the permissible stress, assuming the safety factor was 6, right? We find the force using the cross-sectional area. So the wire is 10 millimeters in diameter. So there's the gauge of the wire, right? In electrical engineering, we call the diameter of the wire the gauge. So 10 millimeters. So 10 millimeters is 0.01 meters. And we divide that by 2 for the radius, right? And we square this and times it by pi to get the cross-sectional area, which is what we did here. Okay. Multiplying this, carrying over and multiply by 53.333 megapascals, we get the force, right? So the force is the max pull, right? Pull is the force, right? So solving this, multiplying is 53.333 megapascals times pi times 0.01 meters divided by 2 squared is equal to 0.00418887 times 10 to the 6 newtons, or 4.19 times 10 to the 3 newtons, and take off this 10 to the 3 and just make it kilonewtons, right? Just make it kilonewtons. Okay. That's how we find the mass. Now there's a question in the chat. So we found the max pull, which is permissible tensile stress, assuming the safety factor was 6, and that permissible tensile stress would tell us the force we're allowed to apply based on the cross-sectional area, right? Yeah. So yeah, it's 4.19 kilonewtons or 4190 newtons. Yep. Whichever one, whichever is easiest for you. Okay. Now, part B says, okay, and also what is the corresponding elongation on a span of 40 meters, right? So 40 meters is the span, is the length. We know strain is this elongation divided by length. Yeah. So what is strain? Well, we don't know, but we do know stress, and we have been given a Young's modulus of 110, so we can calculate strain. So using E is equal to stress over strain, a Young's modulus is equal to stress over strain, we get strain is equal to the 53.33 megapascals divided by 110 gigapascals, right? Mega over giga, right? So we 10 to the power of 6, 10 to the power of 9, 10 to the power of minus 3, right? Times whatever these two divided is, 53.333 divided by 110 is equal to 0.48, right? Times 10 to the 3. That's the strain. The length that was given to us is 40 meters, and the strain, which we just calculated, plugging it into the other formula for strain, strain is equal to elongation over length. Solving for elongation, we get elongation is equal to 40 meters, the length, right? 40 meters times 40 meters times 0.484 times 10 to the minus 3. That should be equal to meters 0.0193 meters. And this, down to millimeters, is multiplied by 1,000 to 3. We get 19.39 millimeters. Okay. Any questions?
So you said that test is on Friday, right? But me said, ain't we have to do the simple machine test first? Then this test?
Well, she sent me an email saying there's a test Friday and the test is on this. Yeah. You guys want to see the email? So I was told the test is going to be on this. So number 17 and 18. That's where the test is going to be.
All right, thank you, sir.
So you won't be having a test for simple machine.
I don't think so. I don't know. So let me write in the
Okay.
chat. Test on Friday. When is Friday? The 22nd. That's on Friday 22nd on stress strength. Focus on 17 and yeah. Okay.
So it's one question, right?
I'd like to think so. Yeah.
Thank you.
Yeah. If you're unsure, verify with Miss. Yeah, because yeah, she never notified me about the test on simple machine. So, you know, and you guys didn't have one last week or the week before. So,
Oh, sorry, remember she said in class last week the test gonna be on stress and strain. She told us in class.
okay, good. Well, prepare for stress and strain, right? Very good. So, no questions on this question here, number 18. It's just like number 17.
So the slide will be sent to us.
Yeah, yeah. We didn't find any mistakes inside. So, yeah, I'll just send it to you guys right after class. I don't have anything to change. No, okay, good. Right. So you guys want me to work number 19 or you guys want to work it?
So that's simple, sir. You're not sure.
Let me try it and give you the rundown, sir.
Yeah. All right, here's a try number 20. Try number 20. If you guys want to try. Because number 19 I worked out. Number 20 I didn't work out.
All right, good.
So number 20. A hollow cast iron vertical cylinder, 3 meters long when unloaded, has an outer diameter of 150 millimeters and an inner diameter of 130 millimeters. Calculate A, the maximum load that can be supported by the cylinder if the stress is not to exceed 80 megapascals, and B, the corresponding decrease in length, assuming E equals 100 gigapascals. So yeah, work number 20. Okay, did anyone get the answer? You see, questions in the chat. Not yet. Okay. All right.
I
So,
reach a certain way, but I ain't sure if I get the right answers.
okay.
Yeah,
So
I'm not sure if I get the correct answer.
just slightly different. So let me draw a diagram here. So it's a cast iron vertical cylinder. Right? So you guys know what a cylinder is, right? Now let's just look at it from above, maybe like the cross section, right? So what that will look like is one bigger circle, right? The outer diameter, and the smaller circle, this inner diameter. So in order to find this area, let me get a different color, is you find the area of the outer circle and the area of this inner circle, right? And then you subtract the two. So maybe this outer circle is A1 and this here is A2. So the area is equal to A1 minus A2, right? That's what you do. So you'd go 2 pi r squared. So that would be not pi r squared, 2 pi r squared. So pi is equal to A1 is equal to pi times 0.15 divided by 2 squared, and A2 is equal to pi times 0.13 divided by 2 squared, and A is equal to A1 minus A2. So you plug this into a calculator, you do that, and subtract it, right? 0.15 divided by 2, square that, times pi, 0.177 minus, no, this is, yeah, and 0.13 divided by 2 square times pi, that there is equal to 0.1637 meters squared, right? This is meters squared. Force. What is force? Well, what are you finding? Maximum load if the stress is not allowed to exceed 80 megapascals. Good. So stress is force divided by area. So this 80 megapascals, 80 times, well, just 80 megapascals. Let's leave it as that. Times 0.1637. It's equal to 13.096. Yeah. Or, yeah. Let me see, there's a question in the chat. Okay, so let me check what the answer is. It times 0.1637. Now this answer here. Is equal to 0.0. Times 0.0043. 98 is equal to about 352 kilonewtons. Okay, so you guys got this answer or a different one?
Yes, sir.
Very good, explain how
I
you
guess
got
in the
that.
previous one, the 13096.
Let me see. Pi times open bracket. Yeah, this here is 0.0132. I missed the 0 here. Yeah, good. So that's that. And then that should give you this and this. So check back, you're working for these two. You get 352 kilonewtons. It's it.
You see,
Yeah.
you have to multiply pi by the diameter separately.
Just give me a second. Yeah, pi by what?
Sir,
You have to
Multiply pi by. I'm not hearing you.
multiply pi by the diameter separately and then subtract.
Yeah. By the two diameters. Remember, because we're finding the area and it's a cylinder, right? The cylinder has an outer diameter and an inner diameter, right? So the outer diameter is 150 and the inner diameter is 130. So that means like the inside is hollow. Yeah, a hollow cast iron cylinder, right? So the inside is hollow, so they don't have any material. So the area is this A1 minus this A2. So the area is inside circle here, right? Minus the area is outside circle. Does that make sense?
Because I had subtract the two diameters and then do pi over 4.
Yeah. Nah, you can't subtract the two diameters because it's area, right? You're not finding a circle whose diameter is 20 millimeters, right? 20 millimeters. That would be a very small, that would be the area of a small circle in the center, not this part here, right? Yeah. So you find area 1, area 2, subtract them, and you get answer. Okay, good. So you guys get this, right?
Yes, sir.
Good. All right, good. What's the other part? B, the corresponding decrease in length, assuming E is 100 gigapascals. Let me get some space. So E is stress over strain, and E is 100 gigapascals, right? Let's just double check, make sure it's the right thing, right? E is 100 gigapascals. So therefore, strain is this 100 gigapascals, and we were given a value for stress. What value were we given? 800 megapascals, right? Not 800, 80 megapascals. 80 megapascals. So therefore, strain should be equal to 80 divided by 100, which is 0.8 times 10 to the minus 3, right? So that's 0.0008. Yeah, that's strain. Now, the cylinder is 3 meters long. We know strain. Yes, more canvas. So the other formula for strain is equal to that elongation or delta L over L, right? 0.8 times the L, so 0.0008 times the length, which is 3 meters, is equal to delta L. So delta L (0.08 times 3) (0.002) meters, or or 2.4 millimeters. That's it. That's all there is to number 20.
So, sir, so you're going to put it in the work with number 20 and send it to.
Yes, sir. I got it for number 22.
Good. 2.4. No money. You guys could do it. Yeah. Number 20 is not coming in a test. But if you wanted
Sir, this 80, right? You multiply it by 80 times 10 to the 3 to get a kg, right? Yeah, the 80 MP. You're going to be 80 times 10 to the 3 to get the kilonewtons.
let me see. So this is 6. So okay. That's 0.004398 times 80. Yeah. Yeah. So yeah, it's kind of like multiplying it. Yeah.
All right.
Get the kilonewtons because it's going to be in M, right? So this here is going to be in mega newtons, right? It's going to be in mega newtons. So 1 meganewton is equal to 1,000 kilonewtons. So yeah, just multiply by 1,000. Sometimes I just work it in my head and then I don't know what I do.
Oh, if you finish up quick. All right, just say one card.
Okay, so and this is the working for stress and strain. It's pretty quick, right? This is stress, this is strain. You divide by 100, so you know that's like 0.8 and times 10 to the minus 3 because
10 to the negative 3, yeah.
and mega, so it's minus 3, right? You divide
Yeah.
it by the 3, so that's 10. So just move this, and you move really quick. Then divide by length, so 0.00 times 3. 3 it's 24, so 0.0024.
Convert to
24.
meters.
Yeah, and then multiply by 1,000 millimeters. Boom. Work the whole question in your head. Anyway, that's it. That's all I have for you guys. Hope you learned something. All right. If there are no other questions, you guys can leave. If you have any
All right,
questions,
thanks.
ask. All right, I'll send this handout to you guys. Which one say? Yeah, enjoy the rest of your day.